Okay. Okay. Right. So thanks for toughing it out to the last talk of the day. We're looking forward to the dinner afterwards. So first off, many thanks to Wayne for organizing this whole thing, and everyone else for coming, and everyone on Zoom for coming. So I'm going to go ahead and start. If this works, does not work. Okay. Yeah. Right. So just to motivate the thing a bit, like we've been thinking a bit about how classical thermodynamics, construed as such, will extend to special relativity. And I wrote a paper about temperature, and today is just following up to think about how pressure would extend to special relativity. So just a brief summary, but everyone's familiar here. Classical thermodynamics is the study of systems, the way I construe it, in thermodynamic equilibrium and how they change under external perturbations. Equilibrium means no macroscopic changes in the thermodynamic parameters, your temperature, pressure, volume, so on. You can think about in cost grading. I'd like to think in specific partitions like this. So for laws, the usual laws, systems spontaneously approach equilibrium. If out of equilibrium, closed systems in equilibrium have a conserved energy, decomposable in terms of heat and work. Closed systems entropy never decreases, and closed systems entropy approaches zero as it's or a constant as its temperature approaches absolute zero. This is just to have something more concrete in mind. I'm not really going to be using these laws except the first law, but the second one here. Yeah. Okay. So what is the scope of thermodynamics is a question I've been thinking about. And one way you find this kind of considerations is in Einstein's autobiographical notes, 1946, where he talks about how classical thermodynamics for him is the only physical theory of universal content, concerning which he's convinced that within the framework of the applicability of its basic concepts, it will never be overthrown. Likewise, or rather, interestingly, 7 years later, Einstein, in his private letter to von Laue, was never publicized till much later on. Liu Chuang did some translations and publicized it in his papers in the 90s. He writes to Laue, "Dear Laue, I hear the voice of my conscience when I remind you of the dispute concerning the rendering of the fundamental thermodynamic concepts in the special relativistic form." He writes, "There's actually no compelling method in the sense that one view of extending thermodynamics to special relativity will simply be correct and another false. One can only try to undertake the transition as naturally as possible." I got cut off here. Sorry. Yeah. So the question is, what led him to think about this, have this shift in his perspective, right? So it leads us to the question, what are the limits of the framework of applicability of thermodynamics' basic concepts? So one specific question you can ask is, does classical thermodynamics extend to special relativity? A more specific question is there a unique way of specifying how a system described in terms of classical thermodynamics transform under Lorentz transformations? And finally, more specifically for today, I will consider the question, does the classical concept of pressure extend unproblematically to special relativity in this sense? My answer will be no, in the sense that, in the sense to be specified. But yeah, so that's going to be the overall picture of the talk. And those who have heard my talk on temperature, you know the strategy is basically similar, and argumentative strategy is the same as well. So what was concluded initially when it comes to temperature or relativistic thermodynamics with respect to temperature? Right, so this project was pursued by Einstein 1907, Planck 1908, but I think Planck's paper actually came out first. So there's because Einstein cites the paper, so it's a bit weird. It was then repeated by Tolman in his textbook, Pauli in his textbook, and they provide these set of Lorentz transformations for thermodynamic quantities. So V being volume, P being pressure, S being entropy. So you get that the volume will contract under Lorentz contraction, pressure stays invariant, entropy stays invariant as well. So the question is, what happens when you're looking at maybe a stationary observer considers the box moving with respect to him, asks what is the thermodynamic quantity of the box if it's boosted away from me, right, with some constant velocity u. So what was concluded initially was that T prime, or temperature in the moving frame, is 1 over gamma of T. So the temperature appears cooler for the moving system. Since then, however, there's been a lot of stuff. So early Einstein, Planck, Tolman, Pauli concluded 1 over gamma T. I think David's paper also concluded 1 over gamma T as the more natural extension. Other people like Ott, Arzelys, later Einstein, Kibbles concluded the other way, that the moving system's temperature is actually hotter, appears hotter to the stationary observer than the co-moving observer. Even later, Landsberg argued that temperature should be invariant under Lorentz transformations. And even later, Einstein suggests that maybe the right way to think about it is to think about the eigentemperature or temperature of the system in its rest frame and not beyond. So like the Lorentz boost of the temperature of a Lorentz boosted system is just the rest frame temperature of the system. So that's how you might think about it. Right. So however, the question is, everyone assumes that pressure is invariant, well, almost everyone assumes that pressure is invariant in the moving frame. Following Einstein's proof in 1907, Landsberg and Johns conclude that this is a generally accepted and valid sort of set of transformations. And today I want to sort of maybe push back on it by considering how it might sort of break at the seams a little bit more than we have thought. But mostly these are things that have been discussed in the 60s and 70s. I'm reporting the stuff that has happened, and then we can see what sort of upshots we might take from this kind of situation. So the way I see it, there are like at least 4 ways to understand the classical pressure. Firstly, in terms of hydrostatics and forces over areas, this is the oldest way of understanding pressure in to my knowledge. Then thermodynamics and the fundamental relation, meaning something like the first law partitioned in terms of your thermodynamic variables. A third one is in more specific terms in terms of the equations of state for thermodynamics, for example, for specific systems, ideal gases, or maybe more de-idealized versions of ideal gas laws. Finally, you can also consider the pressure in terms of continuum mechanics or the stress tensor in the regimes where the mechanical pressure overlaps with the thermodynamic pressure. So in all 4 cases, it's typically accepted that pressure is scalar and isotropic in the classical case, right? There's a consilient understanding of the classical pressure in classical physics. So there's these 4 procedures, and they all pick out the same thing, pressure. So this may be similar to like Billy's talk just now, where there are like 3 ways of doing entropy production, calculating that, but in the new regime, you end up with different understandings of the concept. So there are 4 ways of relativizing the classical pressure, in my view. So one way is to think about relativistic forces over area. This is Einstein's proof. He did it in 1907. Another way to do it would be to think about how to transform the thermodynamic quantities in the fundamental relation itself, using the relations given to you in the fundamental relation without appealing to the mechanical sort of picture. You can also do relativistic thermodynamic equations of state. The idea is just to assume that the equations of state's form holds the same in both the rest frame and the boosted frame. But we're not going to talk about that today. I have some slides later. We can talk about it at the end for time considerations. If there's time, we can talk about it. Finally, there is this relativistic continuum mechanics, basically general relativity or something like general relativity with the stress energy tensor. And I will argue that the consilient understanding of the classical pressure in classical physics breaks down because each procedure tells us something different about the behavior of the pressure, like so, right? So from the hydrostatic relativistic forces over area perspective that Einstein pursued, we get the invariance of pressure. P prime equals P. Pressure is isotropic. It's Lorentz invariant. But there's a curious feature that maybe the system isn't in equilibrium when you boost it. So it'll be clearer once we look at how the boost happens. The second one is in terms of the fundamental relation. Again, the same problem that appears from the first one will show up here. System doesn't appear to be in equilibrium when you boost it from one perspective. Or if you do it the other way, you get P prime equals gamma squared P, or P prime equals gamma squared P plus a U squared P, in the sense that, so given this kind of results in the fundamental relation, you get the idea that pressure is isotropic but not Lorentz invariant as you would have thought from the first perspective. The third one kind of hinges on the temperature transformations. Depending on how you fix your temperature transformations, using the equations of state, you're going to get different behavior for pressure and vice versa. But I'm not going to talk about that in the main part of the talk. We can talk about it at the end. Finally, from the perspective of relativistic continuum mechanics and the stress energy tensor, which is the generalization of the stress tensor, we can get a result that P prime equals to this term here, plus it's not really in equilibrium, or you get a gamma squared P term, which is similar to the second approach, but pressure is not isotropic in this picture in all generalizations. So to start with I'll motivate a little bit why you might think that these 4 are the hinges by which we understand, or the levers by which we understand the concept of pressure. So I'll motivate the concept a little bit, the procedures a little bit. I kind of see pressure as a bundle of these practices, and they kind of together provide the meaning, physical meaning, operational meaning to the concept of pressure in the classical domain. Right, so it's sometimes say that the pressure is defined as force over area, but it's not exactly right or complete. So to make it clear, the classical hydrostatic derivation of pressure isotropy will sort of demonstrate that. So Alan Chalmers, which is interestingly David Chalmers' father, I didn't know that until I read this. So he argues that the first fully modern understanding of pressure as a scalar isotropic quantity was only first presented and argued for in Book 2, Section 5 of Principia, in Newton's Principia. And crucially, this understanding relied on the idea of hydrostatic equilibrium, right? The idea of balanced forces acting on the body or fluid, and explicitly understanding pressure in terms of, but not equivalent to forces over area, in the sense to be specified, right? So the usual proof assumes you have an incompressible static fluid, pushing forces acting on the sphere, perfect sphere from all angles with continuous fluid, and the fluids do not change under volume or density under changes of pressure. That's what incompressible means. And then static means that there are no net flows in the fluid. And once you assume that, then from any point on the sphere, let's see if the light works. Oh yeah. So for any point on the sphere, you can consider how the subspheres are also having balanced forces because they are static by definition, and you can sort of draw circles this way and consider how the equal and opposite forces sort of act all the way to any arbitrary point in the sphere. So you're going to get the fact that pressure is isotropic from give any point of the sphere out inside is isotropic if the fluid as a whole is static and incompressible and has equal forces acting on it from all directions, right? So given this kind of setup where you see this kind of picture, hydrostatic pressure is defined in terms of the magnitude of the forces rather than the force itself, right? So this might be a nitpicky point, but hydrostatic pressure is neither conceptually identical to the incoming forces nor the outgoing forces. It's the magnitude of the balanced forces over every unit area of the fluid, right? So it requires not only the existence of a fluid, but also an external environment acting on the fluid in the way the forces are coming from the environment. So this might seem trivial. Usually you just ignore the environment because they're equal and opposite, so you just pick one and deal with it. But this becomes important in the relativistic domain, as we will see in just a bit. So the idea to take home balanced forces, not just forces over area. So this argument is then generalized to compressible fluids by Euler, providing connections to thermodynamics via gases. And so this shows the consilience of the hydrostatic pressure with the thermodynamic pressure. So the understanding of balanced forces over unit area provides the framework for the earliest derivations of statistical mechanics and how it connects to thermodynamics by understanding forces in terms of average over the momentum of particles hitting the walls, and then considering how importantly in each of the three directions the forces are acting equally, so that you can divide it by 3 and then you get the statistical the mechanical pressure out of it. So it's a simple derivation, but it shows how this idea of forces help to understand the thermodynamic pressure much later on. Let's see. Yeah, so something like this, like an image. Right. So that's the mechanical or the hydrostatic pressure. Moving on to the theoretical sort of thermodynamic pressure. So the isotropy of pressure, as well known, is maintained across the system. You have the pressure is uniform across a system in thermodynamic equilibrium, just like temperature. But the idea of pressure as the magnitude of balanced forces over area does not exhaust the concept in thermodynamics, because pressure also plays a crucial role as an intensive thermodynamic state variable in the fundamental relation of thermodynamics, which is the first law written down in a specific way. I choose the energy sort of representation, right? So Callan, great textbook, says that one standard way of viewing thermodynamics from a fundamental perspective involves understanding the system's conserved internal energy, U, as a function of all the thermodynamically relevant and independent extensive parameters, S, V, particle numbers, N, which exhaustively define any possible thermodynamic state. So you get this kind of usual relation. And in terms of right, if the fundamental relation of the particle system is known, all conceivable thermodynamic information about the system is ascertainable from it. Right, so you can define all these terms, and then in particular you can define the pressure here, right, in terms of the partial differential of U over du over dv, holding fixed entropy, particle numbers, and so on. So you can define that from the fundamental relation. But here you see pressure P is not defined in terms of the magnitude of balanced forces over areas yet. Right? Rather, it's simply defined as a partial differential, the derivative, right, of the particles of the system. However, there's remarkable consilience between them in the classical case. Callan specifically says, classically, the pressure defined by the fundamental relation agrees in every respect with the pressure defined in mechanics. Right? So that's an interesting claim. Right? So this this provides some kind of argument for consilience, right? So, sorry I didn't put it here, but if you start with a box and then you consider a diathermal wall that can move, and then you consider like the entropy and the energy is conserved, and you can let the temperature and the pressure vary a bit, you can prove that the equilibrium state will be the one where pressure on both sides are equal, just like temperature, right? So that gives you the idea of balanced forces in a way, because well, once you equilibrate, the pressures on both sides are equal, so the forces are balanced out. So roughly speaking, right? So that's the consilience between the fundamental relation and the mechanical picture. There are equations of state that weren't mentioned, but just to briefly talk about them for now. I can talk about it later. But with the equations of states, it adds further physical information, because just with the fundamental relation, you can't do anything with the concrete system. You need to plug in the specific equation of state. But that means that the form of the specific equations of state matters, and in fact, it matters a lot for doing specific planetary science or whatever. You need to plug in the right equation of state to do anything thermodynamic. Right? So that's where you might want to think that equation of state also plays an important role that's distinct from just the fundamental equation. Of course, it relies on the fundamental equation a little bit, but it's additional information. Finally, continuum mechanics. It provides a unified framework in which one approaches both continuum fluids and solids. And crucially, from this perspective, pressure is not taken to be isotropic in general. That's an important thing to note. So stress plays a crucial role in this framework, broadly speaking. In consilience with the hydrostatic picture, though, the classical pressure can be understood in terms of one such kinds of stresses, the normal stresses. So again, it's not equivalent to such forces, but to the balanced magnitudes of such forces. Right. This runs contrary to some conventional, maybe textbook views, which might not, obviously we might not want to take textbook for granted, but they do say things like, to say that the pressure acts in any direction or even in all directions, meaningless. Right? Pressure is a scalar quantity. This is a textbook written here. Right? So generally, though, that's not true in the continuum mechanical picture. Right? So the main tool is the Cauchy stress tensor, which quantifies it's a matrix representing the magnitude of the stress in the ith direction acting on the plane normal to the jth direction. I have a diagram here, so you can roughly see what it means. So the normal directions are the normal stresses, and then the rest are like shear stresses. Right. So when do we get the alignment and the consilience? You get it when for a static fluid, right, when no parts of the fluid is moving. So this kind of goes back to Newton's idea, right? A material that at rest only can transfer normal stresses of material surfaces. Then all the shear parts vanish, all the off-diagonal terms vanish, and only the normal stresses remain. And since the fluid is static, all the normal stresses are balanced, and then we can rerun the argument again from the sphere, right? So now we define, given this kind of setup, we define the diagonal elements, the magnitudes of these normal stresses, the balanced stresses, as the hydrostatic pressure. Sorry. Yeah, so you get this kind of relation here, just to highlight it a little bit. Right. So beyond statics, we can continue to use the same approach for non-static fluids if the fluid is ideal or perfect, right, where they have zero viscosity, or if you can, even for incompressible Newtonian fluids, for which we can separate a stress tensor into its viscosity part and the isotropic pressure part, then we can do thermodynamics locally at every part of the fluid, and we can sort of do something like this, right, where D is like the rate of strain, the tensor, quantifying the shear on the system, which you can separate from the diagonal terms, the pressure terms. But you can't do it in general, right? You can't go too far beyond, right? The diagonal terms of the stress tensor need not behave like pressure, nor be isotropic in general. So a general stress tensor for a Newtonian fluid is something like this equation here that I'm going to read out. But you can take the trace and you get this term here, right? This standard derivation, right? But even if you assume that pressure is isotropic, you put it in by hand and define it as the mechanical pressure by dividing the diagonal terms by 3 and saying this is the average, like the pressure, so to speak, we will still find that from this trace term that we saw just now, you plug P in and you compute, you get this difference here. The mechanical pressure is equal to the hydrostatic pressure, which then equals to the thermodynamic pressure, minus this extra term. Right? This is a generally non-trivial term, except for when you assume certain situations. Firstly, why should you assume that the pressure is isotropic when you're out of the static situation? Not clear. And if not, why average over the 3 diagonal components? And Birkhoff says here, regarding that extra term here, right, unless incompressibility is assumed, it's very difficult to incorporate the Navier-Stokes equation into a well-set problem. And to begin with, the mu is often unknown. So Stokes assumed that the mu term here can vanish, or like this whole term, sorry. This whole term here can vanish and then you get the equivalence, right, straightforwardly if you let this vanish here, right? But you can deduce that for monatomic gases, and you can also make a fallacious derivation by defining pressure, which is what I did just now without saying it, right? You can make the fallacious derivation by just defining it as such, but you're not going to get the same concept just from the equation here. You see, they're just not the same concept here, right? So if so, Stokes' equation will follow. If otherwise, we do not know how to. This is important quote. But we do not know how to relate the thermodynamic pressure to the mechanical pressure outside of this kind of situation. So they're not generally the same. But that's fine, right? I mean, like no one expects thermodynamics, the hydrostatic pressure to apply everywhere. So, but this the lesson here is for now is in the cases where viscosity terms become significant enough, then it seems like the distortion experienced by such fluids, in cases like shock physics, but even then in shock physics, apparently you can still try to try to do thermodynamics on it if you assume enough situations. But in any case, if it doesn't work, then it's beyond the domain of thermodynamics, right? We just say, okay, you just can't do thermodynamics in this kind of region. But in the regions where the domains where the thermodynamics applies, then there's still this consilience, this lining up of all the concepts together, right? Continuum mechanics, hydrostatics, thermodynamics, in defining a single pressure concept, the classical pressure, and this is manifest, right? The classical pressure is an isotropic scalar quantity. So in the classical case, these four cases align, and in the domains where thermodynamics applies, so there's no problem there. Right? So the question is, do these different ways, when you generalize them to relativity, do they still align in a nice way? So I argue that they don't. And this is different from the prima facie, different from the hydrostatic, the continuum mechanics case, right? Because there we know that thermodynamics does not extend beyond the static regime or the Newtonian compressible flow regime, but incompressible flow regime. But in the special relativity case, we look at the Einstein project, we might think, oh, there is a way we are trying to find a way to generalize it, so we have to assume that it does apply. So if you assume that thermodynamics should apply in this new domain, then the breaking down should be more worrisome or should lead you to think something otherwise about the applicability of thermodynamics in this new regime. So there is a consilient understanding of the classical pressure in classical physics in terms of a scalar isotropic pressure. But this consilient understanding of the classical pressure in classical physics breaks down in the relativistic regime, as I'll try to argue. Each procedure will say something different about the behavior of pressure. So let's start with the first one. It's generalizing it to the relativistic forces over area, which is Einstein's argument from 1907. So section 13, he adopted a perspective from hydrostatics and classical mechanics, understanding pressure simply as the magnitude of forces over area. And from this perspective, and then he boosted the forces, and then he concluded that the relativistic generalization of pressure is that of a Lorentz invariant quantity, P prime equals P. So you set up like something like a box here, right? And you have forces acting on all these different walls of the box. You can define the Lorentz transformation for the forces, and for the lengths, you get the length contraction, and you get this from considering the behavior of the momentum transforming under Lorentz boosts. So you define pressure, force over area, right? You get the F, L. You start with in the rest frame of the box. You get this definition, and you boost it, right? The gammas will cancel out because one is gamma and one's 1 over gamma. You multiply them, they will cancel out. And then you get the invariance of the pressure here. So pressure appears Lorentz invariant from this perspective, right? Just by considering forces boosting under Lorentz boost, you get the invariance of pressure, right? So that's fine, all good. But before we move on, right? There's a pressure. The thing I want to highlight here is there's this pressure of the 4 force, right? We consider the Lorentz transformation of the 4 force, which is the appropriate, I think, Lorentz covariant object. I think spoken to some people thought the 3 force is the appropriate thing, but I think that we can at least consider the 4 force. dp, where p is the form momentum, over d tau, the proper time. We must also consider the F0 term, the zero component, and how that transforms. Right? It's typically interpreted as energy flux, flow of energy out of a system over time. So since we started with a system in equilibrium, energy is conserved, there's no flow in the rest frame, so the term is 0. But once you boost it, that term becomes non-zero, right? In the boosted frame, instead you get F prime naught equals to this minus u fx. So in the direction of boosting, you will get this extra term from it in the zero component. So you get this term. you can interpret it as work being done by the system to the environment, so it becomes relevant, right? So you get this, let's see, yeah, so you have this, you start with this, then you can consider dE equals to this term that gets you something like a work term because it's a force times the distance, right? So the system initially in equilibrium in the rest frame appears to be out of equilibrium, performing work on its environment in the moving frame when you boost it, even though it's just in equilibrium by definition, right, by stipulation. So that's weird, at least, right? So maybe the question here then is, how do you conceptualize of the boost correctly? So that's a theme that will show up later as well. We'll only transform the forces going from the system to the walls of the box, so the outgoing forces, towards the environment. But recall that the pressure is not, at least I clarified just now, not the force acting on the wall by the system, it's the magnitude of the balance forces. So you need the balance, you need the other side, the light and the dark, so to speak, right? So you need opposing balancing forces. So what we have done is essentially consider how the box would move, how the system would move had the box it was in not moved with it. So we kind of boosted the gas in the box without boosting the box that it was acting on the gas. And how should we move the box? So we boosted just the gas, like this part of these forces. We boost them, you get this minus dW term. But if you boost them with the balance forces, right, you get the opposite term, so you cancels out. So you get the dW instead of minus dW, you sum them together, you get there's no work being done on the system, right? So this is something that's been overlooked, I think, when Planck was doing his derivation, which will get clearer later. So the idea is one strategy is to include the box, right? You can still boost it without including the box, but you have to be careful about what you're doing, right? You have to be clear about what you're doing. So to the stationary observer, it's true that the system sends the box in the moving frame will appear to be losing energy and doing work to its environment, but that's an incomplete description of the system in equilibrium. What made it possible to ascribe equilibrium pressure and more generally equilibrium state to the system was precisely the existence of a box, or more generally environment, right, or adjacent system, acting with equal opposite forces to the system, or more generally equilibrating with the system, right? Once you include the box, the net energy flux is zero. System plus box does not do work, I guess, and the joint system remains in equilibrium. So Penny says something similar back in 1966, right? We cannot think of external pressure as being applied without an internal pressure to balance it almost completely. But if we reject this perspective, we must conclude that the system alone does experience an energy flux, does cease to be or start moving out of equilibrium when you Lorentz boost it. And in this case, Lorentz boosts do not preserve equilibrium on this perspective, even if pressure is Lorentz invariant because of the Einstein argument. Right. So that's the first case. You get the situation that P prime equals P, isotropic, Lorentz invariant, but the system doesn't seem to be in equilibrium. Second case is thermodynamics and using the relativistic version of fundamental relation, and there are two questions that will show up. So Einstein stops at the earlier case. That's where he got the P prime equals P that I showed in the beginning. That's the end of the discussion, and it was never discussed again. And in the 50s, 60s, people have asked questions, but not too much, not in much depth. So we have seen that there are multiple perspectives from which to approach the concept of pressure, all which are consilient in the classical setting. Most prominent is the fundamental relation, and essentially the first law of thermodynamics. However, a similar breakdown of consilience shows up here with respect to the classical pressure, when we consider how thermodynamic quantity is defined in terms of the fundamental relation transformed under Lorentz transformations. So the relativistic mechanical perspective from the previous subsection, the Einstein argument, fails to align with the thermodynamic perspective. So there are two foundational questions here, I think. One is the form of the fundamental relation at all in the relativistic setting, or the first law specifically. And secondly, what is the Lorentz transformation of energy for a system in equilibrium in the relativistic setting? So let's look at the first one first. We've already seen that the energy of the system alone is conserved in the rest frame, but not necessarily when it begins to move if you just boosted the gas without the box. Hence, the change of internal energy for a moving frame is not necessarily conserved, right? So the usual fundamental relation seems inadequate if you started with the du representation. A system not undergoing changes in entropy, volume, or particle number, any classical thermodynamic process can still experience a change in its internal energy. However, so the standard response by Planck is that the system is not in equilibrium in the moving frame until you do something else. So Liu Chuang discusses this in detail, understanding in terms of von Laue's explanation from his textbook that this change has to do with heat exchange. So you need an extra amount of work, given that the system is going out of equilibrium. you need an extra amount of work which is necessary to enable the moving body to release heat with constant velocity. Because of that, its momentum is known to be changed. In order to sustain the velocity as it decelerates from the loss of energy, a force is required, which also produces work. So now he goes on to say, but according to the theory of special relativity, energy has its equivalence to mass, so the system undergoes a change of its mass content, which in turn causes the change of momentum of the system. Without compensation, it will accelerate or decelerate, but if it's not accelerating in the rest frame, it should not do so in any other inertial frame. Therefore, the transferred heat has to contribute an extra amount of its content to doing work in keeping the system from accelerating or decelerating in the moving frame. So this extra amount of work is called translational work, U.dg. Right. So in principle, we can do that. We've seen a lot of talks today and yesterday when we talked about how you can just add extra terms to the fundamental relation. That's not a problem. But Planck proposed to add into the fundamental relation the translational work term, comprising of the intensive-extensive parameter pair U.dg, where U is the system velocity and G is the momentum of the system. It is the work necessary to keep the system without the box in equilibrium, right? So you have to add an extra term there to keep the system from going out of equilibrium. So a system at work requires no extra work, at rest requires no extra work, no additional thermodynamic process to partake in this usual thermodynamic processes like heat transfer with another body as they approach equilibrium with each other. However, the system in a moving frame requires this extra term, translational work in addition to any standard thermodynamic process like heat transfer, in order for the standard thermodynamic process to complete. Otherwise, the system disequilibrates due to the energy flux due to heat transfer. So that's the picture anyway. So the idea is if you boost it, there's this extra term that comes out from the box just by boosting it from some kind of rest frame here to some kind of relatively moving frame. Right. So curiously, Einstein initially did follow the same line of reasoning. He accepted it, but later he changed his mind in a letter to von Laue in 1953. Right? He says, well, when a heat exchange takes place between a reservoir and a machine, some kind of heat sink, for instance, or engine, right, both of them are at rest with each other and acceleration free, and therefore it should not require work in this process. And he says this holds independently of whether both of them are at rest with respect to the frame or at uniform motion relative to it. So he thinks that the boosting of the system should not change the amount of work required to make the system be in equilibrium with the other. So the question shows up for the Planckian view. Where is the work coming from? Why is it not occurring in the rest frame? And the system at rest and relatively moving are one the same, and if you take a passive picture, it's essentially the same system with a different representation. But it's unclear where the work comes from in this picture. Right. So Einstein thinks that no extra work is necessary for the same thermodynamic process, whether it's in the rest frame or the moving frame. And our earlier discussion provides a means to render this perspective clear, include the box, right? And furthermore, generalize our understanding of thermodynamic equilibrium in this case, right? So the energy flux we saw earlier can be rewritten precisely as the energy loss, which supposedly required translational work to compensate. So the loss just now was this term, right? But you get this work term, which is equal to minus U.dg. So there's no, they are the identical term, right? So we saw that considering the box immediately cancel out this term. But then we must generalize our understanding of equilibrium. It's not just a balance of forces on the system, but a balance of energy flux, which is really some kind of force anyway, because it's a force over a distance, and it can also be understood as a momentum flux, depending on how you want to see the same term, right? So on this view, I'll call the Einsteinian view to differentiate itself from the Planckian view just now. We must include the environment, which can be considered the box or the body undergoing heat transfer when we consider a Lorentz boost. Then no extra work needs to be done in the rest frame or in the moving frame. In the rest frame, the forces are balanced. In the moving frame, the forces and the energy fluxes must be balanced if you boost the box together. And in all frames, the system, conceptualized as system plus box, remain in thermal equilibrium, contrary to the Planckian view. So this translational work is just absorbed into what it means to transfer heat or work to a system's environment. It's not a distinct new kind of thermodynamic process. To transfer heat to another body is just to transfer energy plus momentum in the moving frame to another body. There's no extra work or process to be done. At least that's how I would conceptualize the Einsteinian view here. Right? So you boost the system. Let's see if there's animation. Oh, I guess the animation doesn't work. Never mind. So so instead of considering the boost, you consider this energy loss balanced by this other energy gain, and you cancel it out. Right. So there are two fundamental relations as a result of these two perspectives. Right. One is you have to add this extra term, so it's the du, the original du, plus this extra U.dg term. The other one is just du because you cancel out the U.dg with each other, right? And interestingly, if you started with this, you get the original Einstein picture of a temperature transformation, T prime equals 1 over gamma T. And if you did the Einsteinian perspective, which includes the box, you get this T prime equals gamma T, which is different. Like the moving temperature is hotter rather than cooler when you boost it. But first law remains invariant. So if you want to save the first law, you can also just use that as a reason to justify the second perspective as well. So this leads to the second question, right? What is the appropriate Lorentz transformation of energy, right? Actually, both of these, despite the discussion, right, actually lead to the same definition of pressure because it's in terms of du dv. Because you're holding fixed the other terms, so it doesn't really matter what extra terms you put in there. They're held fixed, they're constants. So we know how V transforms, but how does U transform? That will require you when you plug that in to get the solution out. So the pioneers, such as Pauli, Planck, Thomann, as well as others in debate like Kibble, argue that the total energy should transform like this term that I will not try to spell out. So this is this term. There's this extra U square P term in the transformed energy. So this transformation follows directly from a Lorentz transformation of the stress energy tensor for a perfect fluid. Might seem perfectly reasonable, so to speak. But think about what's transformed, right? So when you when you transform the stress energy tensor, you get the 1, 1, 2, 2, 3, 3 diagonals, which represent only the outgoing normal stresses, not the incoming one, right? Because the p's in the diagonal are pointing in some in some direction. Another perspective, the Einsteinian one, is defended by Ott, Azelis, Gamba, Sutcliffe, and others. Also discussed as a viable alternative by Landsberg and Johns. Again, includes the box. So just like how this cancels out the effects of the translational work and kept the system and environment in equilibrium, it also cancels out the second term here because the pressure, the normal stresses of the box acting on the system act in equal magnitude but opposite direction. Net stress is 0. So as a result, you get this nice U prime equals gamma U instead of an extra term like this where there's a U squared P term here. Oh, sorry. So interestingly, either way, however, we do not get the Lorentz invariance of pressure. So both gives you different perspective, but you get different results here. Right? So you just plug using the gamma prime, U prime equals to gamma U. You plug it into the fundamental relation, and you get gamma squared P. Or if you have this extra term, you plug it in, you get this P plus U squared P, which looks a little bit like a moving pressure in aerodynamics, but it's off by a factor of half, not 2. But so I'm not quite sure what to make of that yet. But there's this extra term there, so it's weird. So that's the second perspective, the fundamental relations perspective, where you get either system isn't really in equilibrium, or you get like a P prime equals to gamma squared P, or P prime equals to gamma squared P plus U squared P. So the pressure in all cases are isotropic because it doesn't distinguish directions, but it's not Lorentz invariant. So finally, skipping the equation of state for now, maybe we have time to get there. Let's look at the relativistic continuum mechanics perspective from the stress energy tensor. So the most natural relativization of the 3-dimensional stress tensor is probably the well-known 4-dimensional stress energy tensor. We add the extra terms here. The T00 terms is the energy density. The T0I equals to I0 equals to the energy flux in the ith spatial direction, and also the momentum flux in the ith spatial direction. They are the same. And the TII, the diagonal terms are the normal stresses, as always, where I is not 0. So TIJs are the shear stresses. Right. So it's typically said that the stress energy tensor for a perfect fluid is this rho PPP nice form. So a system with no energy flux with normal stresses with magnitudes P. However, it's not the pressure. The P is not the pressure if the stresses are not balanced, right? Because there's no balance there. It's just forces. So the transformation of this stress energy tensor, you just use the Lorentz transformation, and immediately you recover just by boosting applying the transformation onto the stress energy tensor of this form. You get the result there. Right, U prime equals to gamma U minus U squared PV, which is exactly what we saw from the Planckian perspective earlier on, or we used in the Planckian perspective earlier on. So that's the motivation for using this transformation. Right, since rho prime, the change of rho prime equals to the boosted rho equals to the boosted T naught naught equals to this boosted term here, gamma squared rho plus U squared gamma squared P, and U prime equals to rho prime V prime, you get this extra term that just follows from the calculations. Interestingly, in addition to the fact that it doesn't transform like an isotropic scalar quantity, it doesn't transform like a scalar property, it's not invariant, it also gets this weird directional term here because when you boost it, you only boost in one direction, and the pressure only increases in one direction, not the rest. So it's not even isotropic in this case. Right. So the magnitude of the normal stress in the x direction is clearly no longer equivalent to the normal stresses, magnitudes of the normal stresses in the y and z directions. Even if such normal stresses were balanced with equal opposite stresses, there can no longer be a single scalar quantity which can capture the magnitude of such balanced forces in the moving frame, since the magnitudes are not isotropic in the moving frame. So even in the Einsteinian picture, when we include the box to balance out the stresses, you still get this anisotropy, so to speak. But it's just hidden because you're not going to see it. Right? Furthermore, the system is not in equilibrium because, again, there's this extra term here until we, so there's this extra term here that's not considered. But we can, again, see it as the problem from not including the box. So again, if we adopted the Einsteinian perspective and included the box, consider net normal stresses to be 0. That's what it means for the normal stresses to be balanced. However, it turns out that the stress energy tensor for such a system is not what is typically called the stress energy tensor of a perfect fluid, but the stress energy tensor for dust. Right? So the perfect fluid is like kind of incomplete because it doesn't contain the box, so to speak. So if you contain the box in the consideration, then the pressures, the normal stresses balance out, and you should get a net force of 0 along the diagonal. And if you do that, you get the Lorentz transformation from earlier on, right? If you just boosted this stress energy tensor, you get U prime equals to gamma U. So this is the transformation that people typically use. But to my knowledge, I don't think anyone has discussed this the Lorentz transformation of pressure from this perspective, even though this is usually what they borrow from GR. So that's interesting. The perspective also makes it clear that the forces are not balanced if we ignore the energy flux. If we simply follow convention and define the pressure in terms of the components of T11, T22, T33, the diagonal terms, we find that the system appears to experience an additional normal stress in the x direction, in addition to more anisotropy of pressure. So there's an extra term here, right? So even if we assume that all normal stresses are balanced, such that the net force is 0, the normal stress in the x direction is not balanced. However, you see that these two terms, this term here comes in, right, the extra term here. So the energy density flux is U squared gamma squared rho, which exactly cancels out the increase in normal stress. So even though there's this increase here, it kind of gets canceled out by this term. So our generalized understanding of equilibrium, the system stays in equilibrium with all the forces and density fluxes equally balanced in this new picture. So it seems like there's no avoiding some kind of tension here. Right? Through both perspectives, we learned that the normal stresses are not isotropic, even though they're balanced. And the pressure concept here seems to be vectorial, depending on direction, rather than scalar or isotropic. And this concept of pressure defined still fails to line up with the other perspective and with the classical picture of pressure. That's an argument anyway. So to sum up, the hydrostatic case, we get isotropy of pressure, the Lorentz invariance, but maybe the system isn't in equilibrium. And in the second picture from the relativistic fundamental relation, we get that the system really isn't in equilibrium, and we get this extra gamma squared term here. So it's still isotropic, but not Lorentz invariant. Skipping over the equation of state, for the continuum mechanics case and the stress energy tensor case, we get either these extra terms and system isn't really in equilibrium, or you get these gamma squared p terms and pressure is not isotropic in all the generalizations. So that's roughly it for the breaking down, so to speak. And for the rest of the talk, I'll just briefly talk about some potentially interesting things to think about. One way of thinking about it is to think that, right, of course we can do the thing that I mentioned in the previous paper on temperature. We can be pluralist and say maybe all 4 of these are like good ways to continue on, carry on, and so forth. I want to see what happens if we take it a little bit more radically, so to speak. Right? So maybe you can think of it as having some kind of new or hidden thermodynamic limit. So the thermodynamics does not emerge merely from system approaching the usual thermodynamic limit, where the n over v goes to infinity, but also that there are systems which must be described within some rest frame or like considered in its own rest frame only, and this rest frame must exist, and the theory does not apply in moving frames. Of course, as the speed goes to 0, you can start approximating it with thermodynamics and so on. So maybe you can say that thermodynamics emerge from statistical mechanics only when both limits are approached, not either one. Also, I'm thinking, right? So this is just, I'm throwing it out there. This is just something I thought about, right? Second question is a question about emergence. So Lorentz transformations preserved by construction, the description of fundamental ontology like QFT, but it's not the description of emergent ontology insofar as the thermodynamic system ceases to have a unique description at this level, even though by supervenience you might think that everything that holds at the bottom will fix what happens at the top. So there's a change at the top without a change at the bottom under Lorentz transformation in some sense of change. So maybe there's a breakdown of emergence there. And also you can ask maybe in what sense does the fundamental physics ground thermodynamics? I know Wayne doesn't like the word. So different perspectives says different things about how the more fundamental constitute or compose or play the role of realizing the less fundamental, even if ignored this fundamental relation perspective. Finally, there's a sense in which finally, the thing to think about is the sense in which symmetries preserve appearances. This is something that's been discussed by, for example, Dasgupta in his symmetry-to-reality inferences. Also, Maudlin, Lang, Nozick talks about some similar things. The idea is that if a putative feature is variant, changing in the laws that we have reason to think are true and complete, then there's some reason to think that the feature is not real. So, for example, absolute simultaneity is famously variant in the laws of special theory of relativity. And it's commonplace to think that insofar as you consider those laws to be true and complete, we should think that there's no such thing as absolute simultaneity, right? By endorsing Minkowskian space-time structure, for instance. So Nozick says something similar when he says unified space-time is the true ontological entity for it, only it, and not its lesser dimensional parts, shows something that is invariant under Lorentz transformation. And what it shows to be invariant, although defined by a formula in terms of other quantities, it's not defined solely, or in this case at all, in terms of quantities, they are themselves Lorentz invariant. So Minkowski put forth a strong ontological claim: space by itself and time by itself are doomed to fade away into mere shadows. Only a kind of union of the two will preserve an independent reality. So this leads to a question, right? What about the reality of variance? Maybe thermodynamics could, if you think on some interpretation of the results, like it is variant, like is it therefore not real, or is it something else that needs to be said? For example, also gravitational waves on a suitable choice of coordinates could be made to not be real, to be variant in some ways, right? To vanish in some coordinate choices. Right. So there's some future work that I want to think about, possibly with Sebastian de Margarito Ramirez. So there's something to think about in the future. Lorentz transformations can preserve the laws, for example, the Einsteinian picture, and the fundamental objects, but still fail to preserve a coherent description of the system from below and from above, so to speak. So on such a view, plus our result here, it seems like thermodynamic pressure would not be considered real. Likewise, the temperature, if you accept the earlier papers. So to me, this seems to be a conflation of the fundamental and the real. So Lorentz transformation preserve the behavior and dynamics of fundamental particles, not necessarily the behavior and appearances of things emergent from the fundamental particles, and both can be real in that sense. So Sebastian argued recently that even the laws of springs do not look the same from the perspective of Galilean relativity, so that there might be a case where, well, reality shouldn't be tied so strongly to the symmetry, or maybe it's only like a partial kind of test, not like a full test, and that's fine. Right. So that's it for my talk. Thank you so much, and we can talk about equation of state if you want later. Thank you.
I think we're about to have a similar discussion to the one we had after your LMP talk a couple weeks ago.
Yeah.
I liked all of this very much, but I'm not sure the stuff that preceded it supports the sort of radical conclusions at the end. And here's why. So what happens, and this isn't just in the relationship between non-relativistic and relativistic physics, is that if you look for, if you've got some state theory and then some successor theory, you have some concept in your original theory and say, what's the analog in the successor theory? It might not be unique. Right? So, especially if the successor theory reduces to the first theory in some limit. So, what's the quantity that acts like a mass in the limit v equals 0? Well, clearly that cannot possibly be a unique thing, right?
Yeah.
And so you might say, in pre-relativistic physics, rest mass and inertial mass are the same thing. Right? In relativistic theory, we've got rest mass, and then which is an invariant, and then inertial mass, which is supposed to be the thing that is the m in a three-dimensional f equals ma, and that's clearly frame relative.
Yeah.
And there isn't a question which one of these things is the relativistic analog of mass.
Yeah.
And I think it's confusing to say Nozick says rest mass is real, and for any frame, the inertial reference, the inertial mass with respect to that frame is also real. And maybe the surprising thing is we wouldn't have expected it to be frame relative. So like if I say, well, how far is Eugene? Right? Well, how far from what, right?
Yeah.
And if I say, okay, from this computer in such and such a frame, then there is a determinate answer to that question, and it's just a matter of fact that.
Yeah.
And can we put the Nozick back? I'm sorry, I'm
yeah.
taking too much time.
No, it's fine. Oh, but I need to click on the.
So this is actually going to turn into a question. Okay.
Oh yeah. Okay, yeah. This one.
Actually, okay. I'm hogging too much time. So why shouldn't I just say that the situation is similar to many other things? That there isn't a unique analog. In pre-relativistic physics, there are lots of ways of defining pressure. You have this consilience. In relativistic physics, the consilience falls apart, but then the limit v goes to zero. They become equivalent, and there might be, in some sense, each one of these is an analog of pressure in non-relativistic mechanics, and that's all we should say.
Yeah.
And that doesn't seem to underwrite any radical conclusions about impossibility of doing thermodynamics or something like that.
Oh yeah. No.
Because it is true that, like, you tell me how you're going to measure something, then the theory will tell you what the answer is going to be.
Yeah. Yeah. Thanks for the great comments. So I guess with regards to the last point, yeah. So I totally agree. Like I'm not saying you can't do thermodynamics. I'm saying well, you got to find the frame to do it in, and the rest frame of the system is the one that picks out the right frame to do it in. And when you try to generalize beyond it, you can still call some things pressure, but I guess for now, given the sort of falling apart, then I'm not sure how to carry on. That's the worry I have when we think about generalizing it. It might be that there's one right choice, so maybe David could add to that later. Maybe there is one obvious right choice. I like to think that the fundamental relation plays just as important a role as the mechanical picture in securing what we mean by thermodynamic pressure. And given the two sort of splits, for now at least, then I'm not so sure how to carry on. That's a worry there. So that's why I was thinking maybe if we just stayed in the rest frame or approximately rest frame, then that's fine, and that's where we can continue carry on, so to speak.
Why do we have to stay in one rest frame? If I do it in one rest frame, then the mechanics will tell us how things will be with respect to some other reference frame.
Yeah, but sorry, I guess do we need to? Yeah. Okay. Yeah. So, yeah. No, I guess if you think that all that matters is the mechanics, then that's one perspective you can take. But I think, well, we see how if you just stuck with the mechanics and boosted it, it might not match what you thought thermodynamic behavior would look like, and that's the worry I have there. I thought only in this frame where everything lines up is nice, but yeah. Oh, sorry, we can continue talking about it later as well. Thanks.
So we have an online question. So
Let's go with the online question
since we haven't had many of those yet. We'll do that.
Thanks.
So
I just made up a rule that people who haven't yet asked a question get priority.
You made the rule just after your own response.
There we go.
I call foul.
Is it in text or?
To be fair, I didn't see Giorgio's hand before.
Hi, Giorgio. Do you want to
I accept the
go ahead and ask a question?
Thank you. It's an interesting topic. I work on thermodynamics, and just sort of as a comment, from a sort of, you mentioned relativity of simultaneity, and if you motivate statistical mechanics from something like ergodicity, all microstates are equally likely, and time averages are the same thing as microstates averages. I mean, this last definition, then it's actually kind of trivial consequence of relativity of simultaneity that if something is extended in volume, so like a volume cell, if it's ergodic in one frame, it will not be ergodic in another. Ergodicity becomes frame independent. I mean, this is basically Lorentz transformation. And this, together with the fact that, as you said, if you boost or if you deform a cell, you actually lose intensivity of the pressure. And in global equilibrium, you might have angular momentum, you might have things spinning around. In global equilibrium, defining pressure is actually problematic, just because extended objects in relativity are problematic. Local equilibrium, however, if you can localize microstates to arbitrarily small scales, and if you have instant equilibration, then you will have a uniquely defined pressure. If you don't, so if you have less than ideal hydrodynamics, if you want, you will lose an equally defined pressure. I mean, there is actually been, if you look at the physics literature about relativistic hydrodynamics, recently there has been a lot of activity on the fact that there is multiple ways of defining hydrodynamic frames and writing effective theories of this.
Yeah. Yes.
Pressure in every theory is different, but somehow the theories give the same answer. A lot of, it's technical. I mean, it's not conceptual foundations, but I think there is this conceptual dimension that ergodicity has tension with relativity, and then the whole statistical mechanics apparatus, in particular when we find connections to the quality of conservation.
Right. Right. Yeah. Thank you. The point about ergodicity is interesting. I didn't know about that, but I think I've read the paper you mentioned. I'm not sure if it's the same one. Is it by Kovtun or is it the 2023 paper about the Landau frames and so on? Yeah. So I've been looking at that too. So thanks for reminding me to read it again. Yeah. So it's good to know. Thank you so much. Yeah.
Is there anybody else who has yet to ask questions before?
Yeah, right here.
Well, that has not yet asked a question at all, because David has asked several. That's a Wayne's
It's not a
rule.
just talk.
Well, Wayne implemented a new rule.
Thanks. I have several questions. I'll
Okay.
ask one and get back in the queue.
Yeah.
I'd like to know more about what you mean when you say that systems with certain viscosities are outside the scope of thermodynamics. I mean, on one reading of that seems highly implausible. I assume you don't want to say that if I have a fluid of this high viscosity, I can use it to turn heating to work in a cycle and violence.
Oh no. Yeah.
So what is meant by saying it's outside the scope of
Right.
thermodynamics?
So maybe one way to. Oh yeah. Thanks. Yeah. So maybe one way to say it would be the pressure that's defined there would no longer behave like the pressure you would expect from thermodynamics, in the sense that it's no longer going to be a function of the energy density with the equation of state for a fluid. So that's not going to hold in general when the fluid is moving in the wrong way, so to speak. So it's not going to apply in general, which is the quote I mentioned just now.
But if the fluid is...
Okay, sorry.
I mean, assuming the box is static, if the fluid is moving at all, the system isn't in equilibrium. So definitely equilibrium thermodynamics doesn't apply to it.
Oh, right, yeah. Sorry. I don't mean to say the box is static. I don't mean to mean a static fluid. So I'm thinking like general flowing fluids in general might not have a thermodynamic description. So I was thinking about fluid dynamics broadly construed, which did not be confined to a closed box, right?
Right, but you're
I'll just stand here.
I mean, it's a if I've got a moving fluid, I mean, in some other trivial sense, thermodynamics doesn't apply to it because it's moving. I mean, it might be that you can use considerations of local thermodynamic equilibrium to describe arbitrary small regions of it, but it's going to lie outside the scope of your analysis again, not because it's viscous, just because it's moving.
Right.
It's not an equilibrium, and this is equilibrium thermodynamics.
I see. Yeah. Oh, thanks. Yeah. Yeah. No, that's right. So I guess. Well, is it? I guess yeah. If it's moving, then it's not in equilibrium. Then you can still do local thermodynamics on it, but that might not be guaranteed. I think I'm saying, and for moving fast or crazy enough ways, like a shock wave, for instance, you might not be able to do it under certain circumstances. I think you can still do it, but yeah. So that's what I was thinking when I say you couldn't apply the description. Yeah. Thank you.
Just a question of clarification. This all went very quickly. This is new to me, so I didn't really understand some of it. Help me understand what it means to say that a system that's in equilibrium in its rest frame might not be in equilibrium in a boosted frame. And let me start with it. So if I've got some system and a bunch of, so if equilibrium is supposed to be macroscopically measurable quantities aren't changing.
Yeah.
And if I have a system with a whole bunch of things, measurement apparatus attached to it, and the dial positions or the readouts aren't changing,
yeah.
Then if I boost the system plus the apparatus, it's still the case that the instrument readings are not changing, right?
Yeah, the co-moving.
So isn't it somehow boosting the system but not the measuring apparatus that I'm using to measure these macroscopic properties? Or
yeah.
How am I supposed to understand this?
Right, yeah, thanks. Oh, sorry. Right, no, thanks. That's a good question. Actually, also I was thinking about when I was working this out, it got me confused about this force. Because once you see this force, then the natural interpretation is that there's some kind of work. I'm not sure where the picture is. Yeah, some kind of work being done on the box that. Let me just look at this. Sorry. Yeah. So so you would boost it, and relative to the stationary observer, to which now the box is now relatively moving, it looks like from the coordinates that there is an energy flux. But if you were using measurement apparatus that were co-moving with the box, you would not see any difference. Yeah. So the problem seems to be, if you boosted the box without the measurement apparatus, then you wouldn't see it. Yeah.
Okay.
Thanks.
Then when you say that a boosted system is in equilibrium, a system is in equilibrium with respect to its rest frame and not boosted, then that sounds very paradoxical. But if you say readings of things at rest, of apparatus at rest with respect to the system aren't going to be changing, but when I use the same apparatus, but it's not co-moving stuff, I'm just measuring something different. So some other quantity might be changing. Right? And that sounds less paradoxical.
Yeah. Thanks. Sorry. Yeah, no, that's right. So it definitely seems less paradoxical, but the way they usually talk about it makes it sound. For example, this quote here, right? They will say, without compensation, the system will accelerate. So the idea is, well, not just that it looks different in the frame, but they will think, well, it's going to accelerate in this, or decelerate because of this flux from the way you look at it. Because in this new, like the boosted, relative to the stationary observer, the boosted system now looks like it's losing energy, so it looks like it should decelerate, but well, looking like really just mean it is decelerating or is losing energy in that frame, right? So that's just the description of the system in this new frame or under the boost. So then there's a problem, seems like a weird issue there, which is why they have to fix it or like hot fix it by patching it with the plus UDG term to sort of stop it from moving. And that's the Planckian perspective, basically. Yeah. Thanks.
I want to be back.
Getting pedal.
Sort of draw a disanalogy, I think, between what's going on here and what's going on in earlier work you've also been involved with thinking about how temperature transforms, which I think is possibly salient to asking what you mean by the length transforms here. So, system one we might consider, if you just think about a hot rock in outer space, so the rock, two things about the rock. Firstly, it's the mechanical dynamics that we're studying for the rock Lorentz covariant. secondly, but not independently, the rock has two conserved quantities. It conserves, the physics of the rock conserves energy, and the physics of the rock conserves momentum. So the general term, the handle machinery of thermodynamics, would have us write down something like du equals, well, let's do it the other way around, ds equals beta du plus beta something else dp, just forget the convention, just as the term handle framing.
Yeah.
And then we can ask, well, what happens when we make the reversible active transformation of the system that slightly changes its velocity, and we can do all the kind of discussions of that kind of thing. In this situation, at least the prima facie way we set up a box of gas, it doesn't have this character. The box of gas system conserves energy, but it doesn't conserve momentum because the gas particles bounce off the walls of the box. And so that's why normally when you set up just forget relativity again, when you set up the thermodynamics of a box of gas, you consider the energy as one of the conserved quantities that characterizes the system, but not the momentum or the angular momentum. What you do have instead is you have the parameter that controls the box scale, but just as terms of the mechanical system we're studying, that's being considered normally as an external parameter. It's part of the external dynamics of the system. The mechanics is going to consist of the kinetic energy of the particles in the gas and the intermolecular collisions, but also the potential towards the box. And that is not Lorentz invariant. So of course we shouldn't at all expect that there's any implementation of an active Lorentz transformation of that system. As you say, I mean, obviously that would be out of equilibrium. You're just going to slam the stuff against the wall.
Well, slowly slam it, but
but even so, the only way you're ever going to get a situation where an active Lorentz transformation makes sense of that system is if we change the mechanical system we're studying, and we say now it consists of two subsystems. One is a box, archetype, the hot rock, if you like, only that's hollow, and the other bit is the gas. And now we would be transforming the two. So I think, that's not necessary. I haven't got the full framework here clear enough in my mind to see which of your various moves that prefers, but just in terms of how you'd set the problem up, if we're, as long as we're treating as our system is the gas and the box is treated externally as it usually is, there might be a question passively of how a moving observer might describe that system, but there's never going to be an active implementation of Lorentz transformation. Again, I'm not taking that as in disagreement with anything we've said, just as a sort of second part of the problem.
Great, that's very helpful. Like, I was thinking more of this, I've been thinking about this box a lot, but there's like the box picture, right? So I guess what you said when you think about the gas as the box as a separate subsystem, or I guess the gas. So that would be something like the Einsteinian case where you boost, you're supposed to, when you actively boost the system, you have to boost its environment with it so that it stays in equilibrium with respect to its environment, even if you boosted the whole thing. And the Planckian one and the one that Einstein was considering was something like just boosting the system inside, not around it. But you do get that invariance from that approach. But but from the fundamental relation perspective, you don't seem to be getting that invariance. Sorry, not invariance. P prime equals P, so the invariance of pressure. You don't get that because you get a gamma squared term in this transformation now.
Sure. I could believe that. I guess my point is just to turn the handle of standard mechanics for setting up this system. Either the box is in, and again, you could do this non-relativistically, just Galilean transformations. Either the box is part of the system, or the box is an external part of the potential. If the box is just an external part of the potential, then there's one parameter, box scale, and one conserved quantity energy. If the box is part of it, then there's one parameter. The box scale, which relativistically you have to talk about rest for any measure it in, it doesn't matter. And then there's two conserved parameters, energy and momentum. So even before you start worrying about relativity, just the basic form of the first law is going to look different for the system that just consists of the gas and the system that consists of the gas plus box.
Right. Okay. Yeah, great. That's very helpful. I need to go back and think through how the cranking the time level work. But I see. That's good. Thanks.
Other than Wayne, do we have questions? Get more steps in if you're answering questions.
Okay.
I'm not sure this is related, but I think it is. So if we wanted to ask if temperature is invariant or variant in special relativity, you could just say, well, okay, let's just imagine that the air molecules just are billiard balls, and then they undergo the Lorentz transform. So there are two sets of. You could, instead of talking about temperatures, talk about two sets of your charts with the momentum and position of each air molecule, and you can say, well, on my definition of temperature, what does this collection, what average these numbers, what do I get, and I might use it. I obviously the statistics would be slightly different for the two. Like the observer watching the rocket ship is going to see let's assume they can see the individual air molecules and they're somehow and are calculating their collective motion. And the person on the ship also does the same thing. They're going to have two different sets of numbers. They're going to average them. You could either say, look, temperature should be defined frame relative such that I look at the guy on the ground says, okay, if I had the collection in front of me, in this thing I calculate this temperature, but because I know it's a moving frame, I calculate. Or I couldn't, and that's what it means. It's a question of how are we defining the temperature relative to the collection of numbers we have of basic kinematic values. Is that? So the question is temperature. There's one definition of temperature which is just the average of kinematic without regard to frame of reference, or is temperature would I have to come up with something that tells me convert average to add this factor to calculate average?
Yeah.
Yeah.
Thank you.
Sorry, I hope that made any sense.
No, I got a question. It's related to the stuff I wrote before, so it's helpful to refresh it. If you took the invariant picture, you would say something like, the rocket is flying past me. I just tell the person on the rocket, send it back to me what they measured in their rest frame, like in the co-moving frame with the system, and that temperature is the temperature of the box from my perspective, even though I'm not on the rocket. So that would be like the Lorentz invariant kind of, at least one of the ways you get Lorentz invariance of temperature by fixing it that way. And the statistical mechanical, I'm thinking you are thinking of statistical mechanical approaches to modeling the box. One problem is that while it's unique in the rest frame, the Maxwell-Boltzmann distribution, or the Maxwell-Eugene more relativistic version of the distribution, when you boost it, it's somewhat unconstrained how the distribution should look like. You can think about how if you boosted a black body, the distribution is not going to be the black body radiation distribution, is going to be something else. Right? So there's a question of how to constrain that. That's not clear. Some recent work people have done, they have just assumed that, the equilibrium state picks out a unique rest frame, the frame in which the system is in equilibrium, and you just do set mag on there. But that's just, again, going back to the Lorentz invariant kind of approach, I think. Yeah. Oh, David has a finger.
I mean, just briefly on that black body point, I mean, it might be unconstrained in the sense that it's not going to transform into black body radiation, it's clearly true, but I mean, it's empirically constrained. Redshifted black body radiation sources are extremely ubiquitous and important in astrophysics.
Definitely, yeah. Sorry, I wasn't as precise as I should be. But still, there's an open question of how do you generalize the appropriate statistical mechanical distribution in a moving frame. Yeah, so it's not as clear-cut as it should be. Sorry. Oh, God. What? Wow. How did it even happen? How did it even become like this? Oh.
Who's really good at not doing?
Okay.
This is supposed to be part of a philosophy conference, but I want to step away from the physics and talk about some metaphysics. Can you put that quote up with from Nozick?
Sure.
I found it very puzzling.
Uh-huh. Oh, yeah, I missed that. Yeah, there it is.
Yeah, that one, yeah. And this is more of a question for Nozick than for you, but unfortunately, we're not in a position to ask questions of Nozick. I'm puzzled by the idea of some entity that is a true ontological entity that has parts that are not true ontological entities.
Mm-hmm.
And it raised, I'm a little worried about the prospect that I'm sitting in a chair that is real, composed of parts that are fictions. Sort of.
Yeah.
And there's something really puzzled with it. So he talks about lesser dimensional parts.
Mm-hmm.
Okay. So he's thinking, I guess, about a hypersurface, right?
Yeah.
So suppose I take Minkowski spacetime, right? And I take some inertial frame and I pick out a three-dimensional hypersurface as Vt equals 0 hypersurface.
Yeah.
It seems to me that if the four-dimensional space-time is real, that is also real. It's like the four-dimensional space-time can be completely foliated into parts. Right? And it bothers me that these parts might not be real.
Yeah.
And that hypersurface will not be a constant T hypersurface for any other reference frame.
Mm-hmm.
But I can certainly describe that hypersurface using any set of coordinates I want, and they don't even have to be inertial coordinates. And so he seems to be conflating the mode of referring to something with. So our mode of referring to that hyperplane is not going to be invariant under change of reference frame.
Yeah. Mm-hmm.
But that's a very different thing from saying that hyperplane fails to be invariant. It seems to be he seems to be confusing our mode of referring to something with the thing itself.
Mm-hmm.
So after hearing the question, that's just a comment. So my question is, do you have a comment on what I just said?
I want to make sure we have multiple recordings of Wayne saying he wanted to talk metaphysics. Just in multiple different avenues. Pass that on to
Yeah,
Eugene.
great. Yeah, that's real, right? I great question. I was kind of confused by this quote as well. I guess in the Minkowskian case, I guess you do pick out right, like the rest. Maybe I guess you're not even dead. Yeah. So yeah, I'm puzzled. So I'm not sure what the right answer is. Because that's what got me thinking. Well, maybe what you're talking about is something like fundamentality or something. Like you're not really talking about reality. Like a true ontological entity means like a fundamental entity or something like that. And maybe in that case. The hypersurface is still there, right? So, I'm just thinking through now. I'm not. Yeah.
Yeah, I'm not a metaphysician by trade. The idea that there's a true fundamental entity that can be divided up into parts that are somehow not true or fundamental or something like that. But I'm also aware that there are people who claim that there is in fact only one thing, the totality of everything, and that somehow or another these things that I call things are less real.
Shadows. Sorry. Oh! My God, your glasses. Sorry. Lots of knots here. Sorry. Yeah. No, I think that's right, and like that's partly why I was thinking. Well, even if thermodynamics is variant, depending on how we take away the argument, even if that's the case, I don't think this would hold. It's not like thermodynamics is not real. It's just not fundamental, and that's fine. We know it's not fundamental. And I guess you could say in some ways that the four-dimensional space-time grounds the three-dimensional parts of it. If you wanted to start from, and your criteria for what's more fundamental is more invariant, and then the most invariant thing would be the fundamental. I don't know, maybe it's like someone with a metaphysical interest could like elaborate, but yeah, that's just what I'm thinking right now. Yeah.
questions, comments?
Well, I just want to say I'm glad we have gravity waves, okay.
No, not. I mean, there are worries out there about whether the reality of gravity waves.
Yeah.
That's what you're referring to.
Yeah, I was referring to that. Yeah. So mostly before the observations happen, like so. Nowadays, less. I feel like it's less contentious.
Okay, that's weird.
Yeah.
Because if someone had an argument that gravity.
You know, as I understand the argument against the existence of gravity waves is that you can locally make them go away by going to a freely falling train. But if I bought that kind of argument prior to the observation, then surely I would have nonetheless expected LIGO to do the same thing.
Mm.
I mean, I think it was so.
Yeah.
I mean, I think it was agreed that among people who thought gravitational waves are real and those are not, that a sufficiently strong one could crack rocket Gibraltar.
Right. Yeah, thanks. Yeah, I mean, I don't have much more to say. Gravity waves, not prepared to talk about that here. But yeah. Sure.
Any further questions? If not, maybe. Yeah, well, and very thank you.
Thanks for sharing.